Hi everyone, thank you for coming to my video, and my name is Chi Li from the Department of Chemical Engineering, Texas Tech University. Today, I'm gonna tell you about the conjugate gradient, a very useful method in mathematics and science, which can solve many systems of equations. Now, this is the outline of my talk today. And today I'm gonna introduce the characteristics, algorithm, and example concerning the conjugate gradient method in order to build a basic structure of understanding of this method. First, let's go to the introduction part. As you know, the conjugate gradient method is the most prominent iterative method for solving sparse systems of linear equations. In terms of its history, this method was first developed independently by E. Stiefel in 1952 and M.R. Hastings in 1951. Then, the first report on this method were given by E. Stiefel and J. B. Rosser in 1951. Examples and a numerical test of this method has been done and collected by R. Hayes, U. Hochstrasser, and M. Stein. Now let's go to some details of this method to have a deep look of this one. First, let's go to the targeting problems, which means the problem this method can solve. First, this method is very good to solve large systems of linear equations of this form, ax equal to b. In this equation, A should be a square symmetric positive definite matrix, and B should be a known vector, X is the unknown one. This system arises in many important settings, such as finite difference and finite element methods for solving partial differential equations, structure analysis, and circuit analysis. Second, as you can see, the conjugate gradient method can be equivalent to finding the minimum of this quadratic form. You can also see the derivative of this form, which is ax minus b. This means the minimum of fx is a solution to ax equals to b. Despite of the systems of linear equations, what I want to emphasize is conjugate gradient method is also an important class of method for solving nonlinear optimizations. Now let's come to the pros and cons part. To begin with is the pros. The first advantage I want to mention is the conjugate gradient method can guarantee to converge in n steps, where n is the system size. This is very important for calculations because even before you run the calculation, you can exactly know how many iterations it will go and when it will stop. Rather than compare with the Staples-Stetson method, it may run forever, but the conjugate gradient method won't. In conjugated gradient method, it won't happen. The second advantage is the orthogonal direction. Compared with the Staples-Stetson method, which direction is rather random, the orthogonal direction in conjugate gradient method can be more effective, and it means low memory requirements compared with Staples-Stetson one. Now let's talk about the bad part of or the disadvantage of this method. What I want to say in the disadvantage part is this method only works if you already know the answer. The sentence must be very tricky. Yeah, but what I want to express in this sentence is, as you know from the first value to the second one, then you need to choose the search direction, which should be orthogonal to the previous one. And as you can imagine, there are many orthogonal directions you can choose from that point. However, as I said in the advantage part, the whole steps of this method is fixed. And with the limited number of steps, and in every step, you have to choose the right direction. And you can imagine if all the right direction you can choose, perhaps you have already know the answer before calculation. Now let's see and know about the algorithm of the conjugate gradient method. In order to apply this method to the equation system ax equal to b, you need to start with an initial guess of the solution x0. From this initial guess, you need to do the n iterations to get the final solution. Also, you need an initial residue R0. Usually we set the initial guess as 0 and the initial residue as b, which is the known vector in the ax equals to b equation. And from these two initial value, you can say another initial value p0, which in this algorithm is p1 equals to r0, because in Matlab you couldn't have p0. You can just start with p1. So you can see from the second step, if k equal to 1, which is the first iteration, you set the third direction p as r0, and then after the first step, in each step, you need to update the search direction p. The p is calculated in combination with the updated residue and the previous search direction. After calculating the p in each step, you can update the xk with p and the step size alpha calculated in this equation. You can update the xk in every step, and after xk, you need to update the residue rk in each step, which defined as b minus axk. Now let's see a real-life example applying the conjugate gradient method. Actually, the example I give you here is an optimization example using the conjugate gradient, not like the solving system equations example as I talked before. The reason why I use this example is I want to show you the conjugate gradient method can also be applied on optimization questions. Here, this example is about the geotechnical engineering. Geotechnical engineering is a branch of civil engineering. In this subject, in this geotechnical engineering subject, they mainly focus on the engineering behavior of earth materials. So it has many simulations on computer and calculations on computer. Here, the example is about the finite element simulation in the geotechnical engineering. This equation is just a very simple part of a finite element simulation. We can calculate it with conjugate gradient very well. You can see from the bottom left picture, here is a whole process of the appliance of conjugate gradient. You can see it's gradually converge to the solution. Yeah. The bottom right picture is a figure which shows the paraboloid function, which is a colorful curve, and its way to get the solution. Okay. In this example, we also apply the steep descent algorithm to compare these two methods. You can see the conjugate gradient method converge only in 12 iterations. However, the steepest descent method converge in 158 iterations. You can see the difference very obviously. the conjugate gradient method is really more effective. So thank you for listening for today's video. I hope you guys can all learn something. Thank you.